Okay, so for this assignment, guys, we're dealing with some universal gravitational problems. Force of gravity, universal gravitational constant, mass of the first object, mass of the second object, and the distance between their centers squared. Since big G is a constant, it's not going to affect our problems proportionally. M1, M2, and distance are going to be what we are going to, for the most part, be harping on. So M1, we'll go to this thing right here. The first one is going to represent the first mass, or the mass of the first object. M2 is going to represent the mass of the second object. And D, which is always going to be squared, all right, is going to be represented here by this one. So for now, we're just going to kind of skip over number 2. We're going to skip over number 4 and 5. We're going to get to the ones that we're really dealing with this for. So we're pretty much, you're always going to want to start with this base equation, and then you're only going to change the number 1 based off of if the problem tells you you're changing a mass, or they're changing both masses, or you're changing a distance, or all combinations of them. So in the very first one, two objects of fixed mass, they're moved apart, so they're separated now by 3 times the original distance. So the masses didn't change, but the distance did. And by how much? So 3 times the original. So the distance is now going to be 3, where originally it would have been a 1. So now what we do is we start with this base equation, and then we're going to change, all right, our variables based off of what the problem said. The problem did not tell us that we were changing our masses, so the first mass stays a 1, second one stays a 1. But they did tell us that we're changing our distance by 3 times the original amount. So instead of this being a 1, it's going to become a 3. But distance you do have to square. And then from here, we're going to kind of just play out with this. 1 times 1 is 1. 3 squared is 9. And we can't reduce this anymore, so we are 1/9 the original force. Again, if you're just changing the distance, all right, what happens to that is going to happen with the square of it. So if I double the distance, we're going to have 2 on bottom. 2 squared is 4. It's going to be 1/4. 3 squared is going to be 1/9. 4 squared, all right, on bottom is going to become 1/16 if you don't change the masses. So the further apart you separate them, okay, the more it's going to fall, and it's going to decrease exponentially. Okay. Moving to number 3. Distance of 1 meter separates 2 equally sized masses. Great. Cool. We're setting up with this. If just one of the masses is doubled. So I always make the first mass, the mass that I change first. So if it says one of them is doubled, all right, bet. Now they want to know what the gravitational force is between them. How would that change? Well, if this is the only thing I change, the first mass, M1, I'm going to make that, instead of a 1, I'm going to make it a 2. They never said anything in here that we changed the other mass, so we leave it as a 1. And they didn't tell us that we changed distance, so we leave it as a 1. You have to square distance and then play this out. 2 times 1 is 2. 1 squared is 1. Just reduces to 2. 2 times the force. Okay, so it's 2 times greater, and that goes with what we just did and what we talked about. All right, the gravitational force is going to be directly proportional to the mass. So if I double the mass of something, the force will double. If I triple it, it will triple. Quadruple, it'll also increase by a factor of 4. Got it. Now, let's scoot down here to number 6. Planet X. This has twice the mass of Earth. So our M1 is going to be a 2. And twice the radius. So the distance or the radius here can be kind of used interchangeably. Okay, so it's twice the radius. So distance here will be a 2. If your weight on Earth is 500 newtons, so you're the second object, so the mass of you is not changing because your mass isn't changing here. We're just going to magically teleport you to this other planet, where your weight on Earth was this. All right, so the force of gravity of you on Earth is 500 newtons. What would your weight be on this new planet? All right, so how do we figure that out? Well, the mass of that thing changed. So the first mass, we would make it a 2. It's got twice the mass. Your mass isn't changing, but this planet has twice the radius. So instead of this being a distance being a 1, it is going to be a 2, and you have to square it. 2 times 1. 2 squared is 4. If you can reduce it, please do so.
That's 1, 2.
Yep. 1/2 of the force. Now, we said right here that F is going to be 500, so now we're going to substitute 500 for where F is. And you can do it in your calculators if you need to, but if you don't need to, heck yeah. If you do, it's fine. 1/2 times 500, close it, hit enter, and yes, it will give us our 250 newtons. Imaginary star Z has 1/5 the radius of Earth, so D is going to be a 1/5. But it also has 1,000 times Earth's mass, so M1 is going to be 1,000. How much would a mass that weighs 1 newton on Earth weigh on this star? So F is equal to 1 newton. All right, we're not changing the mass of that object, so what we are going to have is M1 is going to be 1,000. Mass of that other object isn't changing, but the radius of this thing, it does. It's 1/5, but you have to square it. So this is what you wind up with as your equation. Now, to type this in, going 1,000 times 1, cool, it's 1,000. Now we're going to divide that out by 1/5, so 1 divided by 5, squared, close it, boom. And it will be 25,000 times the original force. Now, if it was just, if they didn't change, if the other thing did not change, but the radius here decreased to 1/5, it'd be 1 times 1, all right, which is just 1, divided by that 1/5 squared, which would give us 25. All right, and then the 1,000 times mass piece, that also adds to it. So the original force of this object, they said, right, its weight on the object or on Earth was 1 newton. So on this place, obviously, we just simplify that out or replace F with 1, and yeah, it's just 25,000. Okay. Continuing on. Gravitational force of attraction, all right, of between two objects would increase by what? So again, we're looking at this is your M1. M2, all right, and D, and you always have to square that. If you double the mass for both objects only, so for A, if you double the mass of both objects only, well, 1 and 1 become a 2 and a 2. Nothing happened to distance. 2 times 2 is 4. 1 squared is 1. It would be 4 times the force. So that would be your answer for part A. For B, we double the distance only. Okay, so the masses don't change, so you would leave them both 1s. Distance doubled, you make it a 2. 1 times 1 is 1. 2 squared is 4. Boom. It'd be 1/4 of the original force. C, double the mass of both objects and double the distance. Okay, so both masses, instead of them being a 1, they're going to become a 2. And then you also have to double the distance. So instead of D being a 1, we're going to make it a 2. You still have to square it. You get 4 on top, 4 on bottom. It just reduces to 1, so it would be the same force. And D, double the mass of one object and double the distance. So we're only doubling the mass of one of them. The other doesn't change. And you had to double the distance. 2 times 1 is 2. 2 squared is 4. And this reduces down to 1/2 of the force. Okay. When we get into number 10, how I would kind of go through these here is to figure out, all right, when they say certain things increase by a factor of 2, by a factor of 3, by a factor of 4, they're increasing by a 2, a 3, or 4. If they say they decrease by a factor of 4, well then that would be 1/4. Okay. So again, we still have our mass of the first object, mass of the second object, d squared. Distance between their centers quadrupled. So the word quadrupled means 4 times as much. So which one was it though? Distance quadrupled. So d would be a 4. They didn't tell us anything about the masses, guys. So mass of the first two do not change. Distance though became a 4. You have to square it. 1 times 1 is 1, and 4 squared is 16. Can't reduce that, so it's 1/16 the force. One mass is made 5 times bigger. All right, well, one mass is made 5 times larger. So I would say that M1 is 5. Distance didn't change, the other mass didn't change, so that's why this mass is a 1, this distance is still a 1, and if you play that out, you get 5 over 1, which is just 5 times the force. Now, one mass is decreased to 1/3 the original size. So I'm going to say the first mass is, now it's going to be 1/3. So you can write it out like that. 1/3, the other mass doesn't change, and distance didn't change, so it's that. Anything times 1 is itself, so it's 1/3, and then anything divided by 1 is still itself. So it basically can become, right, 1/3 over 1, which you reduce down to 1/3 the force. Now, if you want to make sure you type it into your calculator, okay, to get it 100% correct, 1 divided by 3, okay, got it. Or we can even throw it in parentheses. It's always a good thing to do with the fractions. All right, times 1, that's the top line, cool. Answer divided by 1 squared. It's going to be 0.33 repeating, which is 1/3. Times the force. Now, if they gave you a number instead of just figuring out what is the ratio for the force, you would then substitute that number in. So we're going to do an example of that. You'll obviously have to finish D and E here. Here, all right, our force is 60 newtons. So when we solve here, all right, and let's say we get 5F, you're going to substitute in at the end that F is 60 and then solve for it like that. So let's take a look at B. One of the masses is halved. So one of the masses is halved. Nothing else happens. So 1/2 times 1 over 1 squared. Now this will come out to be, if you did type it into your calculator, okay, it does come out to be 0.5 times the force. But remember, they want to know what the new weight or the new gravitational force would be. So if the original was 60, you're going to do 0.5 times 60. And you'll wind up with 30 newtons. Let's take a look at letter D. What happens when the distance between their centers is halved? Okay, well then D is 1/2. They didn't tell us anything about the masses, so they would both stay as a 1. Distance, though, is cut in half. So we have 1/2, and you have to square the distance. So if you were to do this in your calculator, right, 1 times 1, got it, it's our 1. And we're going to divide that by, and I'm going to throw it in parentheses, our 1/2. So I'm going to hit 1 divided by 2, which is the same thing as our 1/2. And then I'm going to hit the x squared button. We're going to get our square up, close it, boom. And that is correct. We 4 times the force. Now, the original F is 60, so we would have to do 4 times 60, and you should get what? 240 newtons. We can take a look at F really quickly, and then you guys are going to kind of finish the rest of those ones out. So one mass is made to be 1/3 as large. The other mass is made 4 times as large, so that would be your second M. And they didn't tell us anything about the distance. So we would have 1/3 times 4 over 1 squared. One divided by 3 times, all right, 4. We got that 1.33 repeating. We divided that answer out by 1 squared. You're going to get that 1.33 repeating. Now, if I take that and multiply that by 60, we're going to get a value here of, now I'm going to hit this just times 60, and this is going to kick out here an answer of 80. If you chopped it off and do just 1.33 times 60, and you get 79.8. Yeah. Well, you could leave it as is, but if you use the full 1.3 repeating just from the calculator, you'll get this will come out nice and perfect. If you get the 79.8, technically that would be correct for it. All right, so we do want you guys to complete the rest of those. The only other thing, maybe we'll just take a quick look at this bottom one here of 12. Distance between the center of a spaceship and Earth is increased from 1 Earth radius to 4 Earth radii. So you increased the distance by 4. What would the gravitational force become? Oh, well, you didn't change the mass of anything, so 1 times 1 over, that's an ugly times symbol. 1 and 4 squared is 16, so 1/16 as great.